What is the primary bottleneck affecting the latency for autoregressive decoding of large language models, LLMs, according to the paper?
The primary bottleneck affecting the latency for autoregressive decoding of large language models, LLMs, according to the paper, is the memory read-write operations of model weights rather than arithmetic computations. The paper mentions that decoding with Vicuña 33B on 4 NVIDIA V100 GPUs only yields a throughput of 7 new tokens per second due to this bottleneck. To address this challenge, speculative decoding, SD, techniques have been developed to accelerate autoregressive decoding by verifying multiple tokens generated by a draft model in parallel. The effectiveness of SD relies on 2 primary factors: the gap between the draft model and the target LLM, and the inference latency of the draft model. Researchers often train a tiny draft model from scratch on a large corpus to accelerate large LLMs, but this training can be costly, limiting its real-world application. Additionally, the inference latency of the draft model plays a crucial role in the effectiveness of SD.
How does speculative decoding, SD, aim to accelerate autoregressive decoding? Illustrate step by step.
Speculative decoding, SD, aims to accelerate autoregressive decoding by verifying multiple tokens generated by a draft model in parallel. Firstly, researchers train a tiny draft model from scratch on a large corpus to accelerate large language models, LLMs, from the same series. This draft model generates multiple draft tokens, aiming to bridge the gap between the draft model and the target LLM. Secondly, SD can generate 1 to gamma plus 1 new tokens within each forward pass of the large LLM. The effectiveness of SD relies on the inference latency of the draft model, where the end-to-end speedup ratio is directly proportional to the consistent token acceptance rate. To address challenges, self-drafting methods like LLMA and REST generate draft tokens by selecting text spans from reference or retrieving relevant tokens from the database. Additionally, an autoregressive self-draft model is designed by training a lightweight adapter module on top of a fixed shallow subnetwork of the original large LLM. This approach, named Kangaroo, offers a low-cost way to train a lightweight small model and achieve speedups on SpecBench, outperforming other methods with fewer additional parameters.
What are the main factors on which the effectiveness of speculative decoding relies, as mentioned in the paper?
The effectiveness of speculative decoding relies on 2 main factors as mentioned in the paper. Firstly, it depends on the gap between the draft model and the target large language model, LLM. Researchers often train a small draft model from scratch on a large corpus to accelerate large LLMs from the same series. However, the training of such task-specific models can be costly, limiting its application in real-world scenarios. Secondly, the effectiveness of speculative decoding also depends on the inference latency of the draft model. If the inference cost of the small model is negligible compared to the target large LLM, the end-to-end speedup ratio is directly proportional to the consistent token acceptance rate. This rate is defined as the probability that a certain number of guessed tokens from the draft model are all accepted by the target model. Additionally, the speed of generating draft tokens also plays a significant role in determining the final end-to-end speedup ratio.
What are the main contributions of the proposed Kangaroo framework in the paper?
The main contributions of the proposed Kangaroo framework in the paper include the development of an autoregressive, self-draft model that utilizes a lightweight and efficient adapter module on top of a fixed shallow subnetwork of the original large language model, LLM. This design is shown to be both efficient and powerful, with only 11.3% of the parameters of existing models, like Medusa. Additionally, Kangaroo introduces an early exiting mechanism for generating draft tokens, aiming to reduce unnecessary computational costs on more challenging tokens. The framework offers a low-cost approach to training a lightweight small model by sharing some cache and computation with the large LLM. Experimental results on the SpecBench demonstrate that Kangaroo achieves speedups up to 1. 7 times, outperforming Medusa 1 with 88. 7% fewer additional parameters. Overall, Kangaroo presents a novel self-speculative decoding framework based on a double early exit mechanism, providing an effective solution for accelerating autoregressive decoding of large LLMs.
How is the efficiency of the adapter network architecture in Kangaroo highlighted in comparison to Medusa's heads in terms of parameters?
The efficiency of the adapter network architecture in Kangaroo is highlighted in comparison to Medusa's heads in terms of parameters by being significantly more efficient. The adapter network in Kangaroo consists of only one multi-head attention and 2 normalization layers, which is a simple design but powerful. It has only 3% of the parameters of Medusa's heads. This means that Kangaroo achieves a high level of efficiency with a much smaller number of parameters compared to Medusa's more complex architecture. This efficiency is crucial as it allows Kangaroo to achieve superior performance with fewer additional parameters, making it a more lightweight and effective solution for speculative decoding in large language models.
How is the training loss approach for the adapter network different from maximizing the token acceptance rate as mentioned in the paper?
The training loss approach for the adapter network differs from maximizing the token acceptance rate as mentioned in the paper, in the sense that the paper states that a trivial method for training the adapter network would be to maximize the token acceptance rate across each position. However, the paper finds that the cross-entropy loss exhibits a faster convergence rate. This means that instead of solely focusing on maximizing the token acceptance rate, the training approach for the adapter network involves using cross-entropy loss, which helps the model converge faster during training. By using cross-entropy loss, the adapter network can learn more efficiently and effectively bridge the gap between the self-draft model and the target model. This approach ensures that the adapter network is trained in a way that optimizes its performance and alignment with the large LLM, ultimately improving the overall efficiency and effectiveness of the self-speculative decoding framework proposed in the paper.